Closely related to the permutation statistic that counts excedances in a permutation is another one that counts what are called weak excedances in a permutation. We call I a weak exceedance in a permutation W and Sn if Wi is greater than or equal to I. So it's the same as the definition for exceedance, except that we've got a weak inequality here instead of a strict inequality. So just to remind you, an exceedance if Wi is greater than I. So for example, if we look at S3, the number of weak exceedances are, we ask, is each letter greater than or equal to its position? So 3 is greater than or equal to 1, 2 is greater than or equal to 2, so we've got 2 here. 3 is greater than or equal to 1. I guess whatever's in position 1 has to be greater than or equal to 1. So 1, this is not greater than or equal to 2, and that's not greater than or equal to 3. This is greater than or equal to 1, that's greater than or equal to 2, so we have 2 of them. Greater than or equal to 1, no, and that is greater than or equal to 3. That's greater than or equal to 1, that's greater than or equal to 2. So we've got 2 of them, and here in every letter we've got a position. In every position we've got a letter which is equal to the position, so there's 3 weak exceedances there. So the distribution is 1, 4, and 1. We see 1 a single time, 2 4 times, and 3 once. And the number of weak exceedances plus the number of anti-exceedances is always n. And once again, I did not define the terminology, the notation. So we define WEXCW to be the number of weak exceedances in W. So it turns out that weak exceedances plus anti-exceedances always equals n. And that's because for each position I, we have either that Wi is less than I or Wi is greater or equal to I. We also have that the number of weak exceedances in W is somewhere between 1 and n, unlike exceedances which are between 0 and n. So as we said before, whatever is in position 1 is definitely going to be greater than or equal to 1. So there's always at least 1 weak exceedance. And we could have n weak exceedances if the numbers 1, 2, 3 up to n occur in order, like right here. So it's going to be between 1 and n, unlike exceedances, which is between 0 and n minus 1. That's good because the size of the interval is the same, and we could still conceivably have the result that the distribution of weak exceedances is exactly the same as the distribution of exceedances. And in fact, that's true. So weak exceedances and exceedances are equally distributed on Sn for all n. In particular, the number of permutations in Sn with k minus 1 weak exceedances, sorry, k plus 1 weak exceedances equals the number of permutations in Sn with k exceedances. So the number of permutations in Sn with k exceedances equals the number with k anti-exceedances, which equals the number with n minus 1 minus k anti-exceedances by the palindromicity of the distribution. That is, that it reads the same backwards and forwards. But since the number of anti-exceedances of W plus the number of weak exceedances of W equals n, we have that the number of weak exceedances of W equals n minus the number of anti-exceedances of W. And this should be equals number of anti-exceedances of W equals n minus 1 minus k. So that means that the number of permutations in Sn such that number of anti-exceedances of W equals n minus 1 minus k equals the number of permutations anti-exceedances equals n minus weak exceedances. Maybe I'll write this as n minus 1 plus k. Then if we subtract n from both sides here multiplied by negative 1, we've got this is equal to the number of permutations in Sn such that the number of weak exceedances equals k. Oops, k plus 1. The end.